Hello everyone. So again, welcome back to our latest lecture session. So in the last couple of sessions, we have been looking at applications, right? I think we had different initial compounds that we could put in, mostly with respect to aluminum hydroxide or such, right? Or alum, I believe, right? And then we tried to calculate what the amount of solid is going to, or what's the concentration of the solid that's going to precipitate out from the solution, and what's the amount of the metal still present in the aqueous solution, either in the form of the free metal or in the form of various complexes, right? So today we are going to look at a practical example here, let's say, and here we are going to first try to set it up by hand. We are not going to solve it by hand, at least I am not going to, right? So but I am going to set up the relevant equations by hand and leave it at such a stage where they can be solved, and then we are also going to look at using Vimentech to obviously arrive at the solution within a fraction of the time that we take solving it by hand. But obviously, why do we need to set it up by hand, right? Because you need to understand the basics again. So you will see the difference between using Vimentech and setting it up by hand, again with respect to understanding the basics when we set it up by hand, I guess, right? So again, let's dive into our particular example here. So here we have FeCl3, right, is added as a flocculant. This is a common flocculant, right, to water, right, water treatment plants. So here we also say that the controlling solid is ferrihydrite, right? That's information you always need. And obviously again, why do you need the relevant information about the controlling solid, right? Because the controlling solid and the relevant what is it now, dissociation constant, pardon me, or the solubility product, not the dissociation constant. The solubility product depends on the kind of the controlling solid. For different controlling solids or types of solids, you saw that you had different types of solubility products or solubility constants. So unless you choose the relevant solid, right, or try to approximate it based on the experience that you have had, right, you cannot obviously arrive at the right answer. And in general, as we discussed earlier, in general the amorphous forms, which are the most soluble forms of solid, are formed first, and more or less I believe here ferrihydrite is a good enough example. So within the time frames that we look at in a water treatment plant with respect to coagulation and flocculation, right, let's say formation of ferrihydrite is a worthwhile approximation, right, and is the only solid that forms, right. So first we are going to look at part A, and that says determine the pH and also the dissolved iron concentration if initially 10 power minus 4 molar of FeCl3 is added, right. So here first let's try to understand the system. So let's say you had water and you are putting in, let's say, what is it now, 10 power, or you are adding FeCl3 such that the initial concentration would have been 10 power minus 4 molar, right. So how is the system going to change now? So Cl minus, right, it's relatively non-reactive, at least with respect to the aspects we have covered thus far, and it doesn't play any further role, in general. Let's see, it can form minor complexes, but it usually is not what do we say, relevant in this particular context with respect to the iron anyway, right, the ferric iron. But obviously, as you know, putting in ferric iron can lead to formation of what now? Both the complexes, aqueous complexes that you are aware of. So FeOH complexes are formed. So in effect, when you take out OH minus from the solution and form a complex, what's that going to lead to, right? So that's more or less like an acid, right, for adding an acid, because you're taking out OH minus or adding H plus. So the pH you would expect it to drop, yes. So obviously that's the reason we are trying to look at what's the pH going to be, right. And obviously the other aspect is, other than the relevant complexes and the acid base relevant change in pH, we also know from our precipitation background that ferric hydroxide can precipitate out in the form of ferrihydrite, right. So once this let's say a fraction of this 10 power minus 4, right, this is Fe total, let's see, Fe total is 10 power minus 4 molar, right. So we know that Fe total will be in the form of Fe total after it reaches equilibrium in the aqueous phase and also in the solid phase, right. So here obviously you are also concerned with what is the dissolved iron concentration, as in what is Fe total in the aqueous phase, right. So obviously for that you need to be able to calculate your Fe total that has, or the ferric iron that has precipitated out. Once you calculate the amount of iron that's precipitated out, you can subtract that from the initial or Fe total and then get the Fe total in the aqueous form, right. So obviously again keep in mind that when we are talking about dissolved iron concentration, we are also taking into account not just the free metal but also the complexes, because they are also in the dissolved phase, right. and different forms of iron. So we consider even the complexes to be different forms of dissolved iron. So again, how do we solve for pH, and also obviously the Fe total aqueous. So obviously what's our approach here? We always have the component balance, right? So for this particular example, I guess I'm going to set it up in a relatively detailed manner, but I'm not going to solve for the relevant values. That I'm going to leave to you, let's say, as part of the homeworks or such. But with the VMinTech, we are going to go through with the calculations, right? So component balance, right? So first component balance, we need to identify the species. So species are the what is it now? Relevant compounds that would be present once the system has reached equilibrium. So obviously what do you have? Obviously you always have H plus and OH minus, and then you will obviously have the ferric iron, right? Free metal, and then you will also have the relevant complexes. And I think from our background, ferric hydroxide complexes, usually there are 4 types formed, right, that are usually predominant, and that's what I'm going to list. If you are not sure, obviously you can look up the relevant standard books and find out how many constants there are, right, and then come up with the relevant number of complexes. And also obviously you are going to have, or we are going to consider that what we say the solid is precipitating out. So I'm going to go ahead with the assumption that solid is formed. So first assumption is obviously that I'm assuming that solid is formed or precipitation occurs, right, or the precipitation occurs. So thus with that in mind, I'm going to list my species. So H plus, OH minus, and then the free metal, right, and then I'm going to list all the complexes, right, with respect to Fe and OH, and 2 plus charge, Fe and OH twice plus 1 charge, Fe and OH thrice the complex with 0 charge or neutral, Fe, OH 4 and negative charge, and obviously I'm going to be left with my solid Fe, OH thrice and the solid, and obviously Cl minus, but in the case that we are considering, right, you know, Cl minus we are assuming that it doesn't play any further role, so actually we can neglect Cl minus 2. But obviously if you are looking at charge balance, you would have had to consider that. But for further calculations, as you see in all the species that I have listed, right, Cl minus does not play any further role, so I can neglect the role of Cl minus in my further calculations. So obviously what are the components here? So usually we choose H plus, right, and we choose the metal, and obviously Cl minus, but I'm going to neglect that later on, right. So we are done with listing the species and then the relevant components, the building blocks, right. So and then what next? I need to list my formation equations, as in how am I going to form the relevant species from my components. So here we are going to only work it out for the non-component species, as in I am not going to show the relevant formation equations for H plus, Fe3 plus and Cl minus. So we are going to have to look at the formation equations for OH minus, FeOH 2 plus, FeOH twice plus, FeOH thrice 0 charge, FeOH 4 negative charge, and then the solid 2, right. But I am going to start neglecting Cl minus from here on, right. So am I missing anything else? Okay. So how do I use or come up with these particular species from the components? So that's the formation equation, right. So here obviously H2O minus H plus, right, and here it's going to be equal to Fe3 plus, and I need to have 1 OH minus, right. So that's going to be equal to what now? Plus H2O minus H plus, hopefully that does resolve it, Fe3 plus H2O minus H plus, so 1 OH minus, right. So here Fe3 plus I need to in effect have 2 OH minus, right. So that means I am going to have 2 times of H2O, anyway I will write this as 2 times H2O minus 2 times H plus, right, and Fe3 plus would be, FeOH thrice would be 3 times H2O minus 3 times H plus, and Fe3 plus 4 times H2O minus 4H plus, and Fe3 plus 3 times H2O minus 3 times H plus, even for the solid, I guess, right. So now let me just tabulate this, I guess. Let's just list the tableau here, and keep in mind that I'm starting to neglect the role of Cl minus here because I haven't listed that in any of the species here. So I'm going to list only the two components here, which are H plus and Fe3 plus. So again, need to list all the species. So again, because I said I'm going to do it in a relatively detailed manner here, I'm going to set this up. So I'm just obviously listing all the species here, right? And once you have the relevant background, we could or we can skip writing the formation equations and just directly list the relevant species and the tableau, right? So anyway, for now I'm listing this. So how do I get to H plus? I need 1 H plus to form 1 H plus and 0 of Fe3 plus. How do I get to OH minus? I look at this particular equation, right? So I need minus 1 H plus and no Fe3 plus. Obviously Fe3 plus 0 H plus is required, 1 Fe3 plus is required. How do I form this complex? Again, I look at the relevant equation here. So 1 of ferric and 1 minus 1 of H plus. And so similarly 1 minus 2, 1 minus 3, 1 minus 4, and here 2, it's going to be equal to 1 and minus 3. Again, that's from this equation for the solid 2. And obviously I need to add the recipe species, right? And what's the recipe species here? Whatever it is that I'm plugging in initially, not plugging in, pardon me, adding to the solution initially. So that was FeCl3, if you remember from the question, right? We are adding FeCl3, right? And I guess I should have written that here. How can I form FeCl3 here? So I need, let's say, what is it now? Fe3 plus 3Cl minus, right? So if I had listed Cl minus, this would have been 0, 0, 0, 0, 0, 0, 0, 0, but I could have listed Cl minus, which I haven't listed here as one of the species. Well, let me go ahead and do that. Cl minus 0, 0 and 1. And so here what's the balance? FeCl3, any role of H plus here? No. So that's going to be 0 here, and Fe3 plus is 1 from here, I guess, right? And how much Cl minus is that? It's 3, right? So with that I have the component balance equations as we saw earlier, because I did not consider any Cl minus related species here, right? Chloride related species here. I'm setting that up as just Cl minus would be equal to 3 times the FeCl3 concentrations. That's obvious, right? Anyway, how do I solve for this? Let's say just for purposes of FCl total is equal to what now? Cl minus, concentration of Cl minus, right? That's what you have from the total component balance here. And obviously what is that equal to? The recipe species, that's equal to 3 times of FeCl3 concentration, right? So then I can calculate that. So I'm done with my one of the variables here. But obviously I have the other two component balance equations. So I guess for lack of space, I'm going to list them in the next particular slide here, right? So first let me try to list H total and then Fe total, right? H total. So it should be H plus minus OH minus, right? Minus the complexes, right? FeOH twice and I believe plus 1 charge obviously, minus Fe or 2 times now, right? Minus 2 times FeOH, I guess a minor issue here, 2 plus, right? FeOH twice and plus here, minus 3 times FeOH thrice, 0 charge, right? Minus 4 times FeOH 4 minus, right? And I believe the last one was the solid, 3 times FeOH thrice. This is the solid. Now keep in mind that this was the aspect that we talked about earlier, right? So in the earlier classes, if you remember, how did we set it up with respect to the solid now, right? So in general, when we talk about the concentration of this particular complex or such, we are talking about the number of moles of that particular complex in dissolved in a particular volume of water. But here with respect to solid, we do have it as a variable, but keep in mind that you need to get your basics right, that it's not dissolved in water, it has precipitated out, or it's in a different phase, right. But for our need to calculate the relevant amount of solid that has precipitated out, we are having a variable here, and the units here obviously are going to be moles of solid that has precipitated out from the solution for the volume from which it has precipitated out, right. Anyway, that is a basic what we say understanding that you need to have. And Fe total, so anyway, how did we get this particular equation now? Obviously, right, from this particular set of component balances, right, and that is what we have. And what is that equal to? And anyway, I will plug that in later, or not really, I am going to just show that here right now. And obviously from my recipe species 2, what do I have H total to be equal to now? H total is equal to 0, right, which is equal to 0 times FeCl3 naught, right. So that is equal to H total is equal to 0, and now Fe total is going to be equal to Fe3 plus concentration. Again, how am I writing this, or how are we writing this? I am just balancing this particular set of terms, right. So Fe total is in the form of what now? Fe3 plus, FeOH2 plus, FeOH twice with the plus 1 charge, and so on. So this is nothing but the component balance here, right. So Fe3 plus what else please? FeOH2 plus charge plus FeOH twice plus 1 charge plus FeOH thrice no charge plus FeOH4 negative charge, and also the solid, right. And obviously again, what is this equal to? And again I am going to go back to here. I see that it is 1 times the recipe species concentration, right. So that is equal to 1 times FeCl3 naught, right. So here let us list the number of variables we have. So there are 1, 2 and 4 complexes, right. So that would be 6 plus 1 7, 7 plus one other free metal concentration. So we have 8 variables, right. But I have only, how many equations do I have so far? I have 2. So I have 8 variables and I have 2 equations. So I still need to come up with 6 more equations, right. So how do I come up with that now, right. So obviously I have one equation, Kw is equal to H plus into OH minus, right. So that is one particular equation, yes. So what are some of the other equations here? Obviously I still need to come up with 5 more equations. So you know that for each of these 4 complexes I have the relevant beta 1 star, beta 2 star, beta 3 star and beta 4 star, right. And how do we come up with this, or what is the relevant equation for these beta 1 star, beta 2 star and so on? If you remember, we had with respect to complexes we defined 4 types of coefficients, right, and different books have different kinds of these coefficients listed, but in general for the component balance it would be worthwhile to look at beta 1 star and so on. Why is that? Because beta 1 star, if I remember right, it is the direct addition of the protonated ligand. So let us see one particular relevant equation here. Let us see how am I going to form, let us say my complex here I am going to consider for beta 1 obviously should be FeOH2 plus. So it is going to be in equilibrium with, I start with the metal, right. So beta 1 star direct addition does not make too much sense here because it is only one particular ligand here, but here beta 1 star refers to the protonated ligand, right, protonated ligand. So ligand is OH minus, the protonated form would be H2O, right. So to balance it out obviously I need to have H plus here, right. So again for the relevant beta 2 star what would the equation be? Fe3 plus plus, so it needs to go to FeOH2 plus 1 charge, right. So here the aspect of direct addition comes into picture, so it is going to be 2H2O, right, direct addition to Fe3 plus rather than coming through or utilizing FeOH twice and so on, right, FeOH2 plus. Again Fe3 plus direct addition of the protonated ligand would leave me with 2H plus, right. So again, I am not going to list them for the other equations, but let us just write down what is beta 1 star going to be equal to. That is going to be equal to the concentration of H plus, right, into concentration of FeOH 2 plus, right, by Fe 3 plus. Yes, and for beta 2 star, what is it going to be here? It is going to be equal to H plus square, right, it is from this equation obviously, times FeOH twice positive charge by Fe 3 plus. Again, in the same manner you can list it for beta 3 star and beta 4 star, but you get the picture. So now we have how many more additional equations? We have 1 earlier, so 2 plus 1 from Kw, water dissociation constant, and beta 1, 2, 3 and 4. So I have 4 more equations here, right. So 2 plus 1, 3 plus 4, I think I have only 7, right, but I still need to have 1 more equation to be able to solve for this particular set of problems, right. And what is that equation now, right? And keep in mind here obviously we have a particular aspect related to precipitation, right. So obviously you know the solubility product FeOH thrice the solid will be equal to, or will be in equilibrium with, pardon me, right, Fe 3 plus 3 OH minus, right. So you know that this K solubility product for ferrihydride, you can get the constant, right, is going to be equal to nothing but Fe 3 plus times OH minus 1 cube by the activity of the solid, which for a pure solid you know is going to be equal to 1. So now you have the additional or the final equation. So you now have 8 equations and 8 variables, right. But obviously what are you going to do? You are going to transform all the variables such that, right, these 2 equations such that you are going to only have, let us say, either of Fe 3 plus and the solid, FeOH thrice the solid, right, or just H plus and FeOH thrice solid as the 2 variables, right. You are just going to plug in the relevant what do we say equations into these 2 particular equations such that you are only going to narrow down the number of variables to 2 variables, right. That is just substitution, which I am not going to go through here obviously. So but because our particular question asks you to solve for pH, right, so obviously it makes sense to look at or have the relevant variables to be H plus and FeOH thrice solid, right. So and then I can solve for it, and if the particular solution for FeOH thrice the solid turns out to be negative, what does that mean? That means obviously the solid doesn't precipitate out, and you need to not consider the solid and then redo the calculations, right. But obviously if it turns out to be positive, what does that mean? I have arrived at my true solution, right, and obviously then I do not need to go further anywhere, right. So let us say I am assuming that, or it should turn out to be positive in this case. So you will now get the Fe total in the solid, right, and by solving for H plus I can also calculate the pH. So I calculate the pH and Fe total solid, and what does the question ask for? So it says calculate the pH, which you are able to do, and it asks for the dissolved iron concentration. And how can I get that? So we solve for pH from H plus, right, and dissolved iron nothing but Fe total in the aqueous phase, that is equal to Fe total minus the iron that has precipitated out, and this is something you just calculate, right. So with that, at least by hand, right, this is the procedure to go about solving for your particular this particular scenario, right. Again, keep in mind that we started with the assumption that the solid is going to precipitate out, right, and if that variable turned out to be a negative value, then you would have had to remove that particular variable, meaning you would consider that obviously that no precipitation has occurred and go through with the relevant calculations, right. So now obviously you know this is by hand, and you can use solver to solve for those 2 equations. Solver is a function in Excel that you can use, wherein you can set or ask Excel, let us say, to change a set of cells such that another cell will be either equal to minimum, maximum, or in this case equal to 0. Anyway, that is for you, you can look it up in Excel, I guess, right. But now let us see how to set it up by vMinTech, right. So what are the aspects that we need to look for? I need to give the total component concentrations. So I know that, if you remember, that H total is equal to 0, and Fe total was equal to, I believe, 1 times FeCl3 naught. That was equal to, what's the concentration that we plugged in, please? 10 power minus 4 molar, 10 power minus 4 molar, right? And also Cl total is equal to 3 times FeCl3 naught, right? And that's equal to 3 into 10 power minus 4 molar, right? And obviously you also need to specify the solid, and we know that ferrihydrite is something that you need to consider. So we are going to just plug in these total components into the Vmintech and specify ferrihydrite as the possible solid, I guess, right? So let's move on to Vmintech. So Fe total, first let's look it up, and that's out here. I'm going to use millimolar units to make it easier for me to plug them in, I guess. So 0.1, it was 10 power minus 4 molar, right? So 0.1, add that to the list. And Cl total, what was that equal to? And Cl total was equal to 0.3 millimolar, 0.3, add that to the list. And I need to specify the possible solid phases. So obviously that's going to be equal to ferrihydrite, right? So I'm going to add that, and you can see that it's listed in the possible species present in the problem. Back to main menu, and I'm going to run my Mintech. So obviously because we put in ferric, right? Ferric can or not can, you know that it will form the complex or can precipitate out. More or less it's going to remove the OH minus from the solution, right? So thus obviously that's going to bring down the pH, and that's what you see here. The pH is now 3.537, right? And then also look at amount of finite solids, and ferrihydrite is formed at almost 10 power minus 4, 9.7 into 10 power minus 5 means more or less 10 power minus 4, as in almost all the ferric iron that you added has precipitated out, right? So let's look at equilibrated mass distribution. So here for Fe3 plus, the percentage dissolved is only 2.2% of the total that you plugged in initially, but the percentage that has precipitated out is 97.7 or 97.8% of the total iron that you plugged in, right? So almost 98% of the ferric source of ferric that you plugged in, Fe3 plus, precipitated out, right? And only 2% is present as or in the dissolved phase in the various complexes. Again, within this 2%, let's see which particular aqueous complex predominates. So I think we can look at that here, and I think it's FeOH, right, with +2 charge, if I am reading that right. Yes, FeOH with the +2 charge is relatively predominant, right? So again, this is what we expected, and that's what we saw here too. So obviously the dissolved, so the question asks for, if you remember, pH. So pH is 3.537 and asks for the dissolved iron concentration. So that's going to be equal to 2.2 into 10 power minus 6 or 2.3 into 10 power minus 6 molar units, right? Okay, so I guess with that I will be done with part A. So in the next particular session we are going to solve for part B, I guess, right? And with that I guess I bid adieu and thank you.